queuing analysis, queuing model. What is a queue? What is a queue? It's a line. It's a sequence of people. It's not only people, it can be things that are waiting their turn to be processed or to be attended to. So you can see different examples of queues. Okay. Where are places that we queue a lot? Who can give me an example? Give me practical areas of places where either human beings queue or items queue. Where are some of the places that we queue? Where are some of the places? Someone just said MTN office.
Airport check-ins.
Please raise your hand. If you're actually talking there, you got to raise your hand. Okay. Other than that. So MTN office, good. Pooling stations, good. Banks, good. Watches seller joint, good. Flight landed. So that one is not for the human being, is the flight, is the aeroplanes. So the planes, okay, also queue. Okay. Airport check-in site, that's human beings, good. I want more that are not also human beings. More places that are not human beings, but they are items or certain things that are rather queuing. Bar station. Bar station, you mean human beings queuing at a bar station to take the truck. Okay. Production lines. So by saying production lines, I'm sure you are talking about if you have some bottles, okay, the bottles are queuing. Bottles are queuing right now. Then lorry stations. Okay, so the lorries are queuing. So yeah, if you go to the motorway previously, you will have, cars are queuing, to be able to be served. So these are all places. Queuing is the same as waiting. Queuing is the same as waiting. So queuing theory is the same as waiting in line theory. Okay. Queuing theory is the same as waiting in line theory. Okay. So take note that queuing is a practical thing that happens in real life systems. The most important thing now we want to look at is, and by the way, you also queue at a hospital. Okay. Sometimes you have to queue at a hospital and then you get served. So many things happen when we talk about queuing. It's very practical. There are three components of the queuing process. The first is you have the items that are queuing. In fact, we're going to discuss the three components very soon as we go further. So these are examples that most of you have spoken about. But why do we study queuing? Why do we try to understand the queuing theory? Why do we have to understand waiting in line theory? Well, the reason is because if you're a manager, you got to use it to decide, because time is being wasted and time is money, they say. Actually, time is not money. But the more people spend time in a queue, the more revenues are being destroyed, because the customer is king and the customer is likely to spend his time somewhere. For example, I don't like going to the bank at all. So my bank pays me when I don't come to the bank. Because when I go to the bank, I will expect them to pay me. So I don't want to go to the bank. And in some countries, the customer is even paid for not coming to the bank. And so if you try and push customers' time, you're going to lose the customer. And when you lose the customer, you lose the money the customer has. Okay? Also, when you reduce the queues to a tolerable level, you will raise your revenue as a result of that. And you will see the connection between cutting down queue, raising time, and raising revenue. We'll look at that analysis as we go. So there are three components of queuing model. These are the components. The first is known as the arrival rate. Please write it down. Write it down in your book, arrival rate. Arrival rate is represented by lambda. What is arrival rate? In fact, if you can move faster with these points, that is when you will understand queuing model. The arrival rate is the number, and it is human beings, take note, is the average number of customers, whether the customers are human beings or items, the average number of customers arriving within a specified period of time. Remember that one we're looking at the Poisson distribution. Do you remember the Poisson distribution? Okay, we said that it carries this idea of something happening within a specified period of length or time. That's the same principle here. That lambda, okay? So the lambda here is the mean, the average number of customers within a specified time. So let's say within an hour, if it is within an hour, we say 200 customers in an hour, 600 customers in an hour. That is arrival rate. So note that is the average number of customers. And then you also have the service rate. The service rate or the mean service rate is also the average number of customers, but those being served. Guys, note something. The average number of customers that are being served within a specified time period is not the same as the average number of customers that are arriving within a specified time period. But what you know is that the queuing system is made up of those that are waiting and those that are being served. Write it down. The queuing system is made up of the average number of customers waiting per the time period they are waiting and the average number of customers being served. So if you take, for example, when you get into the bank, you are in a queue and you are sad, but the other person who is being served, because he is being served, he's not that sad because he's no longer in the queue, he's being served. And so the entire queuing system is made up of those within the queue plus those being served. My question I want to ask you is, which one is more? Is it the arrival rate that is more, or it is a service rate that is more? Which one is more? And of course, I will ask you why. So it's better to rather think about a why than to tell me. Is it the arrival rate that is more, or the service rate that is more? Which one does the company have control over? Which one must be higher? Which one must be higher? Which one must be higher? I can see most of you are writing, arrival rate, arrival rate, arrival rate. Okay. Unless you raise your hand and give me a reason, okay, it doesn't mean that you are correct, though. Neither does it mean that you are not correct. Okay. Why? Which one must be higher and why? Someone says is the service rate. Someone said it's arrival rate, and then the person rather gave a reason for the service rate. No, it's not because one is a subset of the other. One cannot be the subset of the other. Take note. I told you that they are separate. They are both subsets of the queuing system. So which one? If someone says, because more people have issues. More people have issues that require attention. So where would they be? If they have issues, where would they be? Okay. They are still going to arrive within the arrival section, or they are still going to be served within the service section. My question is that which one must the company try to double it? Okay. You got to think, guys. You got to think. You got to think. Why? Which one? Why? Okay. So here's the thing. The arrival rate must be smaller than the service rate. The arrival rate must be smaller than the service rate. Why? Because if the service rate is not higher, then queues will build up. A lot of queues will build. Imagine you enter the building and then your service rate is 0 because you've not opened the door. what happens is that you're going to have a lot of people. So my question I was asking you is that which one must be more? Which one must be more? And the service rate must be more. Because if the service rate is not more, the lambda, which is arrival rate, will exceed. And then, of course, we are talking about from the perspective of the company. And so the mu, which is the service rate, must be higher than the arrival rate. It must be higher than the arrival rate. So please take note, keep that in mind. Okay? And so your goal, of course, naturally, you can have a situation where the lambda is more than the mu, okay, where the arrival rate is more than the service rate. But eventually, even though at the beginning of, say, a bank, they've not opened the door, so obviously the lambda will be more than that. But which one must be more? But towards the end of the evening, you will notice that the service rate has taken care of all the arrival rate, because that is what must be more. So the service rate must exceed arrival rate, because by that 3 p.m. towards the evening, all those that arrived have been served. So keep that principle in mind. It is crucial. It is crucial. Okay. So this is the entire queuing system. And I want you to take note of the queuing system that I spoke to you about. If you look at this queuing system, guys, you have those that are waiting. Okay, these are the arrival rate. And then we have those that are being served at the tilt. This is the service rate. Okay. And the entire system is the two of them. Of course, we have departing customers, those who have arrived and those who have arrived and been served already. They are not part of the queuing system. They are the departing customers. But this is what a company has to deal with. Okay? The queuing system, the arrival rate or the arriving customers, and then the service rate or the serving customers. Okay. So with that in mind, with these basic things in mind, in fact, the other part is the entire period of time that it takes to do that. So let's look at the main elements of a queuing system. The key points you should keep in mind before we go into the operating characteristics. First point is that anytime you're looking at queuing system, queues build up or they form because people or things arrive at a service faster than they can be served. That's why queues build up. Now, not that it was deliberate. Sometimes it's deliberate. Sometimes it's simply because they've not started serving. They've not started serving. Obviously, the lambda will be more than that. But that is because they've not started serving anyway. You know. The other part is that most peak operations have sufficient server capacity to handle the customers in the long run. And you will see that in the long run, everything is sorted. So even though it might be that in the beginning, somebody mentioned election, so many people will build up in the morning, and then it will look like things are bad. In the long run, the organization is supposed to have sufficient server capacity to deal with everything in the long run, not in the short run, in the long run. And you will notice that eventually people get saved. So the issue is not about the fact that you will not be handled. It is about the fact that I want you to handle me now. I want you to increase the server capacity in the short run, not in the long run, because in the long run, we sort it. But that, not that. The key thing is that customers don't arrive at a constant rate. And it's true. Some customers will come now, the service will be idle when some customers are not in. You know, when they are busy, that's when some. So certain customers don't come at a constant rate for the company to know that, okay, everybody is going to come at this time. No, they come at different rates. So you do not control that. Okay? But if you know that, you know, customers have been distributed and told that these customers must arrive at this time, these people must arrive at this time, you know. That is why traffic build up. Traffic build up because of all of this. Sometimes early in the morning, okay? But if all of us are going at a constant rate, then traffic will not build up. Okay. So we are going to look at a single server system. Okay. That's what we're going to look at. These are the factors that characterize waiting line system. We're going to look at a single server system. In other words, we are looking at a situation where there is only one server. This is for simplicity. In real life, there are multiple server systems. Teller number 1, please. Teller number 2, please. Teller number 3, please. There's multiple server systems. The single server system has an infinite calling population. It is also based on first come, first served basis. Okay. And there are other things that can influence the single server system: the queue discipline, the nature of the calling population, and the first thing we mentioned, the arrival and the service rate. All of them affect the single server system. And the discipline in which the queuing works is not only first come, first served basis. Sometimes you can rather have last come, first served basis. Have you seen some things like that? Yeah, like emergency situation, last come, first served basis. Emergency situation. Sometimes you can have service in a random order. Okay, so this one comes, is served, another one comes, is served, because they are. For example, I go to the hospital and my issue is about, let's say, physiotherapy. Okay, physiotherapy is free. And even though I just came, they just call me. But then you have come, but they've not called. It's random. You can have a situation. And then you have by appointment. Okay? Specialized barbering shops do that. Priority. Okay? By appointment. You get that one as well. So all of these are part of the queuing discipline. And then finally, the calling population. Okay? That is the source of the customers. It can be finite or infinite. As for the arrival rate and the service rate, we've spoken a lot about it. But 2 things you got to know about arrival rate. The arrival rate follows a Poisson distribution. In fact, I said it earlier. The arrival rate follows a Poisson distribution. Okay. What is the Poisson distribution? If you guys can remember probability, that would do. The frequency, okay, at which the customers are arriving. Okay. They are arriving at a waiting line, in the order of the Poisson diagram. Now, this is a typical example of the Poisson diagram. Okay, it goes up like that. So it's rising and rising. It's rising and falling, but rising and falling at an increasing rate. It's rising and falling, but rising and falling, not falling, but rising and stabilizing at an increasing rate. It's rising and stabilizing, rising and stabilizing, rising and stabilizing, rising at an increasing rate. And that is a Poisson distribution there. Then, so that's arrival rate. And you can see that it's always like that. You just check a bank. The people arrive, you deal with it, then they arrive, you deal with it, then they arrive. Okay, so it follows a Poisson distribution. But when you look at the service rate, it's the opposite. Because you are cutting down the number. Okay, so as the service will rather start at a higher level. If you look at arrival, yeah, the arrival starts at a lower level and then it starts building up. It starts building up. It starts building up. It starts building up. Okay, but that is not the same as the service. The service, it was by the time the service will begin normally at a higher level and then it starts going down. So that follows a negative exponential distribution. A negative exponential distribution. This is a typical example of a negative exponential distribution. It starts like that and then it starts coming down. So sometimes you see, if it is a bank, you see the teller coming. People are already waiting. Then it starts cutting down the number, okay, from a higher to a lower level. That is how they are distributed. These two work together in a queuing analysis. Okay. What is the essence of our presence here? The essence of our presence is that there are certain operating characteristics, formulae, that are used in a queuing model, and they are used to understand the queuing analysis. And these 8 operating characteristics, you got to know them. So please, when I mention each one of them, write it down, because the more you write each one of them down, the more you will understand it. Okay, and each one of these will be explained as we go forward. The first is in fact, this time we have to change it. Okay. The first is the probability that no customer is in the queuing system. So take note, the probability that no customer is in the queuing system. The probability that no customer is in the queuing system. Now watch the word. If no customer is in the queuing system, it means that the server is idle. Keep that in mind. And you will see that this operating characteristics will agree with the last one we'll talk about, which is characteristic number 8. If there is no customer in the queuing system, it means the server is idle. But if there is a customer in the queuing system, it means the server is busy. So take note of the first one. Okay, the probability that no customer is in the queuing system. Now, it is given by 1 minus lambda over mu. What do you think will be lambda over mu alone? Who can guess? If the probability that no customer is in the queuing system, which is also the probability that the server is idle, and that is 1 minus the arrival rate divided by the service rate, then what do you think is this one, the arrival rate alone divided by the service rate? How will you interpret that? You got to be incredibly great. You got to be following me to be able to answer that, actually. What is this? What is lambda over mu? What does that mean? I'm not looking at a number. I'm looking at you talking and telling me what does that mean? What does the lambda over mu mean? Well, the lambda over the mu will surely be the probability that the server is busy. So if this 1 minus the lambda over mu is the probability that the server is idle, that is because no customer is in the queuing system, then the lambda over the mu alone will be the probability that the server is busy. That is, there are customers in the queuing system. Keep that in mind. So that is the first operating characteristic. That's the first formula you got to know. Remember that the lambda is the arrival rate. Remember that the mu is a service rate, and they are all averages. So mean arrival rate, mean service rate. Let's go to the next formula. I hope you've written this first one. Next one, the next operating characteristic is the probability that a certain particular number of customers are in the queuing system. The probability that a particular number of customers are in the queuing system. Look at the latter part here. So this one is lambda over mu raised to the power n, that's that particular number. So if you believe that a particular number of customers are in the queuing system, and that is 12 customers, then you are going to have lambda over mu raised to the power 12 multiplied by the probability that there is no customer in the queuing system. This is the probability that the server is busy. This is the probability that the server is busy, but is busy with a specific number of people. That's what it means. You know, because when you tell me that he's busy with how many number of people? That is the probability that the server is busy with a particular number of people. So watch, the first two formulae are all about probabilities. Let's look at the next two. The next two are not about probability. They are about the average number of customers. Take note. They are about the customers. Formula number 3 is L equals to lambda over mu minus lambda. It is the average number of customers in the queuing system. Guy, anytime you are talking about a queuing system, we are talking about those waiting plus those being served. Those in queue plus those being served. And the formula for that, if it is about number of customers, it is L. But if it is only those in the queuing system, watch this. This one is those in the queuing system. That is both waiting and then being served. But if it is only those waiting, then this L will have a Q. attached to it. If it is only those who are waiting, then the L will have a Q. So if you find, and this is important here, if you find L, which is those who are waiting plus those who are being served, and then you go and find LQ, and I'll show you LQ very soon, which is only those who are queuing, where the Q means queuing. And I now ask you, tell me the average number of customers who are being served. That's an exam question. Tell me the average number of customers who are being served. What you got to note is that you got to know those who are waiting plus being served, and then those who are waiting, you take the difference between that. Okay. So let's say that those who are waiting and being served is, say, 4.5. Okay. I mean, I'm just trying to be non-integer, but let's make it an integer. Let's say it's 12. And then those who are waiting alone, you got that to be, say, 9. Then those who are being served is going to be 3. That's what it means. Okay. So take note that the L is both those waiting plus those being served. And so if we have those waiting, which is also called LQ, then if I want to know those being served, it's just the difference between that and LQ. Let's look at those being served. Okay. So this is a formula, by the way, those who are waiting and being served. And then this LQ is those who are only waiting, or those in the queue. Those in the queue. So you can see that we have the 2 formulae on probability. We also have 2 formulae on customers. And for the customers, it is both those in the waiting line plus those being served, and then only those in the waiting line. So that's formula number 4. Take note of that formula. And remember, each one of them is using, the formulas are all about the arrival rate, the service rate, manipulating them, squaring some of them, as you can see right here. Formula number 5 and the formula number 6 also move together. They are not about a probability. They are not about the customers. They are about time. That is average time. And it's the same thing as the one before. Average time a customer spends in the queuing system. That is average time a customer spends waiting and being served together. And that is W. There's no Q attached to it. When there's a Q attached to it, it means that you're only looking at those in the queue. That is those waiting. So in this W, which is a time, you are dealing with 1 over mu minus lambda. That is those being served plus those waiting. And as long as you have that for the time, then we can only now go to WQ, which is this, which will look at those waiting alone. Write this formula, the WQ, is going to be one of your most important formulas we shall use today. Those queuing, those waiting. Write it down. Write it down. Please write it down. Okay, so now you have a beautiful situation of WQ and W. We have LQ and L. Okay? And then we have the probability, the P naught and Pn. Let's go to the last 2. And you see some similarity somewhere. So the last 2 is probability again. Okay, but there's something interesting about this probability. And it is this fact. The probability that the server is busy. And if you look at this carefully, you will notice that we've seen it somewhere. The probability that the server is busy is the same as something we call a utilization factor. The probability that the server is busy means that the customer's got to wait. The customer has to wait. Because I'm busy, I'm being utilized, you got to wait. And it is just a lambda over the mu. So take note that the server being busy is the same as, the customer will. Sometimes you ask the question, what is the probability that the customer has to wait? Well, that is the same as the probability that the server is busy, which is the same as the utilization factor. If I am being used, which is this U, then it means that you got to wait. And that is a probability. If I am idle, which is the next one, then it means that you got to come. You can be served. So the probability that the customer can be served is the fact that I am idle. So I is 1 minus the probability that you are being utilized. Customer is being utilized. So these last two are probabilities. So these last two, you also have to know them, okay, because they are really, really cool. Okay. Now let's get into the nitty-gritties. We are going to now do some work. Please, I want you to understand queuing model better. And in order to understand queuing model, always learn this. Learn how to convert minutes to hours. Learn how to convert hours to minutes. I want to do some quick exercise. And this is what I normally do to elevate your mental consciousness. How many minutes are in 2 hours? Who can tell me? How many minutes are in 2 hours?
You see, someone like your sister. See what she does?
Look at that. Okay. It's 120. You see, that one, you thought of it quickly. You thought of it very quickly. How many hours are in 200 minutes? How many hours? If you don't take it, that one is usually difficult for people. How many hours are in 200 minutes? You have to have a certain number in mind anytime you are dealing with these. What is the number? What is the number you must have in mind anytime you are dealing with this? There's a particular number. What number is that? And please, when I say convert something to minutes, you don't tell me this hours, this minute. No. When I say convert something to minutes, you're just telling me the 30 minutes. So don't say 3 hours, 20 minutes. No. If it is 300 minutes, you say 300 minutes. Okay, not there. Excellent, Achampo. Emmanuel, the number you must always have in mind is the number 60. Why? Because every 60 minutes makes an hour. Every 60 minutes makes an hour. So let's quickly do some exercise further. What is 0.25 hours in minutes? Quickly. This, once you got to have the answers very quick. Follow the crowd. What is 0.25 hours in minutes? Quick, 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 quick. You see, you are using if less more divide, if less more divide, if more less divide. You're using that in your head. You see, somebody just got it wrong. Whilst others are getting 15, somebody got 150. It's very easy to get wrong. This whole idea of if more, less divide, it always helps you. Okay. So how will you do that? Well, the moment you know, and I'm giving you a final clue for you to get these things quickly. The moment you know that we are in hours, we are converting it to minutes. The moment you know we are in hours and we are converting it to minutes, okay, then you must know that we are either multiplying or we are dividing. And you got to know one of them. Okay, we are in hours. We are converting it to minutes. So immediately you multiply. We are in minutes. We are converting it to hours. Immediately you divide. That's a clue. That's a clue. From hours to minutes, you multiply. From minutes taking to hours, you divide. And that's how you get it quickly. Are you with me? So a calculator must be with you, and then you quickly answer these things fast, fast, fast. Otherwise, you're going to delay. And this is not where you want to delay because the real ones are coming. These are just the basics. The basics. Okay, let's take another one. 10 minutes equals how many hours? Quickly, you have 2 seconds. 10 minutes equals how many hours? Sharp, 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 sharp. Hurry up. Divide, multiply, divide, multiply, divide, multiply. That's a clue. That's a clue. Okay, good. So you're getting it 0.167 hours, 0.167 hours. Okay. 40 minutes is how many hours? Quickly. 40 minutes is how many hours? If you are here with us and you think that you're not going to go through this yourself, I'm telling you, your brain will not be activated by these principles. But if you go through this with the rest, you will always crack this code. 0.667. Very good. The moment you spend more than 5 seconds on the thing, you are losing. Let's go to another one. 0.6 hours is how many minutes? 0.6 hours is how many minutes? Slight delay, you're in trouble. Very good. Very good. Some of you are really cracking. Stephen is like this, is going so fast. Okay. Very good. 36 minutes. Okay. Next one. Now, we are going to take a situation where you would now do some analysis. So with this conversion now in your mind, guys, you should now be able to calculate arrival rate, which is lambda, and service rate all the time. So I'm coming to give you a quick one. If it takes 5 minutes to serve a customer at Papaya, how many customers are served in an hour? Now, first of all, this question, is it asking you about a lambda or the mu? Quickly. Is it asking you about a lambda or is it asking you about a mu? Quick. Hurry up. Lambda or mu, lambda or mu, lambda or mu. Okay. Is a mu, okay? Is a service rate. Because, and you see, you got to know that the service rate is mu. But not just know the English name, but also the Greek name that is a mu. So you know that this question is asking you about the service rate, which is a mu. So with that in mind, you use the principle of if more or less divide and have the minutes to hours in mind, because it says if it takes 5 minutes to serve a customer, how many customers are served in an hour? So now it's changed the minutes now quickly to an hour. So you have to now know this in minutes. And fortunately for you, it didn't say 3 hours, but you rather said in an hour. So you know that that's how many minutes? 60 minutes. Because you must all be in the same unit of measurement. If the first one is minutes, the second one must be minutes. If the first one is hours, the second one must be hours. Okay. So how many customers are served in an hour? Quickly, who can tell me? 12 customers. Exactly. 12 customers. Okay. Again, if more or less divide. So this is how you normally write it. It takes 5. This is how you write it. It takes 5 customers. Well, what it is. It takes 5 minutes. I'm just showing you a simple way. That is if you are lost about how to calculate this. Okay. 5 minutes to serve 1 customer. Okay. So how many customers? So how many customers are served in an hour? So you write 60 minutes under the 5 minutes. Okay. And then you find your X because you're looking for customers. Okay. So whatever you're looking for should be under where the customers is the 1 customer. And at this stage, you can multiply. Cross multiply 5 times X equal to 60. Okay. So you now have 5X equals to 60. Divide both sides by 5, and then X is going to be 12 customers per 60 minutes, or 12 customers per hour. That is how you work it out. Okay, so those ones are basic. I want you to just know that they're basic. Okay, let's look at another one. A system has 1 facility, 1 service facility, and this can serve 10 customers per hour. The customers arrive at an average rate of 6 per hour. What are the chances that a customer has to wait? By the way, this is an exam question. What are the chances that a customer has to wait? What is it asking you? Look at your operating characteristics. What is this question asking you? Who can tell me? Quickly, what is it asking you? It's giving you certain things. What is it asking you? What is it asking you? Arrival rate? No, it's not asking you about arrival rate. What is this asking you? What is it asking you to calculate? Probability that the server is busy. Perfect. That's what it's asking you. The probability that the server is busy. So the customers got to wait. Oh, great. The probability that the server is being utilized. So it's asking you of the utilization factor. Look at your formula. Look at your formula. So straight away, you know that it's asking you for U, the utilization factor, U. And what is that U? We know that it's equal to the lambda over mu. And so you got to make sure that they are all in hours or they are all in minutes. In this case, fortunately, they are all in hours, so you don't have a problem, okay? Because it says a system has one service facility that can serve 10 customers per hour. So the customers are in hours. Then customers arrive, that is a lambda, okay, at an average rate of 6 customers per hour. And so you should find the utilization factor. So how do you do that? You get 6, which is the arrival rate, divided by the service rate, which is a mu, which is 10. And that gives you the utilization factor. Do you get it? That is how you work this beautiful thing. And of course, when you look down here, you get it. You see, it's a matter of knowing the word. They are keywords. It's not all the time you're going to see the word service. Sometimes you see the word serve. Okay? But you got to understand it generally. It's not only serve and service. Look, think of synonyms that can indicate that somebody is being served. Okay? So you go to a restaurant, okay, and one of the waitress decides to provide the customer with something. That word provide there gives you an idea of service there. So it's not all the time it's got to be serve. Sometimes the word might be different, but your general understanding will help you to be able to get the picture and to be able to zoom into understanding. Now, regarding the arrival, normally it is always that keyword. But you can say that motorists get to the station. That word is arrive. So it's not all the time also you will see the word arrive. Sometimes you might not see the word arrive, but think widely. Think widely. Okay, let's go to the next one. These are all building up towards a key point. Okay, these are, by the way, these things, even though they are all building up, they're all exam questions. Let's take the next one. The ticket booth on Eberoho campus. The booth, so you know a booth, okay, at the motorway or something. It is operated by one person. That word operated, she didn't give you a clue. That person is selling the tickets for the annual Yam Festival. The ticket seller can sell an average of 15 customers per hour. On average, 3 customers arrive to buy tickets each 15 minutes. Now, while this one was in hour, this one is in minutes. Of course, you always have to convert it to hours. Keep that in mind. Okay, now we go to the question. Question 1, determine the average time a ticket buyer must wait. Watch the words. Determine the average time a ticket buyer must wait in the queue. So he's asking you to find the average time a customer or a buyer has to wait. So this question is asking you about what? Which of the formula is he asking you? Which of the formula is he really asking you to do? You got to know that first before you even start it. Which one is he asking you to find? Which particular formula? You know the formula have got symbols, okay? Some of the formula have got, P naught, you got PN, you got L, you got LQ, you got W, you got WQ, and then you got U, you got I. These are the formula. Which one? Which one is he asking you to find? WQ, perfect, Stephen. You're thinking, you're really thinking. That's really good. So how do you know that? It says average time a ticket buyer must wait. So he didn't say Q, but you know that the word wait is the same as Q. And so it's asking you to find the WQ. And so immediately, now that you know that it's asking you for the WQ, you go look for the formula for the WQ. Okay. Of course, if you have a formula book, you use a formula book. If you don't have a formula book, you think, depending on which point. So what is the WQ? This is a formula for the WQ. This is the reason why I told most of you to write it down. But the WQ requires that you know your lambda and you know your service rate. But they must all be in the same unit of measurement. So you go back to the question there. The question says what? It says that you have 15 customers that are being served per hour. So straight away, you can see that the service rate is equal to 15 customers per hour. So that one is already in hours. So that one is cool. What about the lambda? The lambda is not in hours, it's in minutes. So you got to bring it to hours. And you are told that there are 3 customers that arrive every 15 minutes. And you want this in an hour. You want that in an hour. So if 3 customers arrive every 15 minutes, how many do you think would arrive in an hour or in 60 minutes? Because you know 60 minutes is an hour. Okay. If I multiply the 15 by 4, I get to 60. Okay. So if I multiply the 3 by 4, I get my customers. Do you see the trick? I mean, there are several ways you can work this, but again, you can use if more, less divide, if less, more divide. Okay, the same thing. And the answer is going to be what? So just to go basic, there are 3 customers every 15 minutes. So the question now is how many customers every 60 minutes? If more, it will be more. Okay. If more, the less will divide. What does that mean? If more, the less will divide. What does that mean? If more, the less will divide. So that word, you look at it, okay, which one goes down? That's the meaning of divide. Okay. That divide is which one goes to the denominator. Which one goes down to the denominator level. That's the meaning of divide. So as it stands here, you know that this one counts. So as it stands, you just cross multiply. And then you find the value. 60 times 3 gives you 180. 180 divided by 15. Okay, and that gives you 12. And therefore, the lambda will be 12 customers per hour. That's how you get it. Now they are all in hours, so you are cool. So now you can go and then find your WQ. And the WQ, always check again and write it down. Okay, is the lambda over mu into bracket mu minus lambda. That's it. And you know the lambda here to be what? 12. You know the mu to be what? 15. So you know you're going to have 12 divided by 15 into bracket 3. Because the 1 in the bracket is there. So it means that you're going to have, now you can use all of your analysis. 3 goes here, 5, 3 goes here, 4. Then you have 4 over 15. And then you can find the answer. Now, whatever answer that you get here, okay, remember it's time, queuing time. So let me just delete this. So whatever answer that you get, by the way, you have it, everything I've said, you have it here. Okay. Whatever answer that you get is in minutes. It's in hours, sorry, because everything was in hours before. So you get this one in hours. And now, if you want to have the answer in minutes, you multiply that. Okay. If you want to have that, you multiply that by 60, and then you can get it in minutes. You will later understand why, after getting the queuing time in hours, you multiply it. You multiply it by 60 to get it in minutes. You later understand. Anyway, so that's it. That's how you get this one, 5 marks. But let's go to the next part of the question, which says, determine the portion of time the seller is idle. Again, what formula is this asking you? Determine the portion of time the seller is idle. Yeah, let me see. I, exactly. And I is given by what? Idle is given by what? Don't just sit, talk some. 1 minus the utilization. And the utilization itself is what? Say some. Say some. Look at your formula. Type some. It will help you. It will help you. Okay. So that is lambda over mu. Okay. So basically what you are looking for, you're looking for I, which is 1 minus lambda over mu. You see why I told you to write your formula. Okay. So how do you get that? Well, we already know the lambda from the previous. We know it to be 12. And then we know this one to be what? The mu to be 15. So it's going to be just 1 minus 12 over 15. And that is basically 3 over 15. That is your answer. Remember, it's the word portion means percentage. The word portion is percentage. So when you do that carefully, you see that we're going to have a small portion, which in this case, it will be 20%. 20%. That's it. Now, we go to the last part of this before we come to the real deal for today. Last part says, the management of the campus likes to have its operators working 80% of the time. So watch the word. They are working. They are working. That is utilization. They are working 80% of the time. They are working. They're working. They're working 80% of the time. So utilization is already 80%. But here's a question. What must the service rate be in order for the operators to be as idle as management would like? He says, what must the service rate be? He's looking for the mu. But look at the question carefully. He says that we know that utilization is the arrival rate divided by the service rate. And you have been told that the utilization is 80%. So 0.8 is equal to the arrival rate. And we know the arrival rate is what? 12. You are being asked to find the service rate. Change of subject. Now, why do we know that? Even though he said that what must the service rate be in order for management to be as idle? Idle here means that you can choose to use the idle formula, or you can choose to use the utilization formula. You get the same answer. If I was to use the idle formula, it's the one above here. So it's going to be 1. Okay. If we are talking about idle, then if the people are working 80% of the time, it means that they are idle 20% of the time. So it will be this. And now you have 1 minus the 12 over mu. So you should still look for mu. Either you look for mu here, okay, or you look for mu there. You get the same answer. If you find this mu from here, you get 15. And if you find the mu from here, it will be 12 divided by 0.8. That will also give you 15. So it was a very tricky question, but a very easy question to let you know that if I know the utilization percentage, I should know the idle percentage. That will give you the answer. Anyway, so when you look at that one, it's a very simple thing, and you get this one. So if you want this last part, it's simply asking you for the u, and so u becomes 15. Cool, isn't it? Now let's get to the real deal. But these are important ones to help you going forward. Let's look at the real deal. In real life, though, management want to use a lot of approaches to cut down the waiting time. In fact, we said that from the onset, that the waiting time is too bad. Sometimes the customer will wait for, especially in government institutions, the customer will wait and wait and wait. And you want to really cut down, especially in private organizations, you want to cut down because of competition. So you want to reduce the waiting time, the queuing time, the WQ, the waiting time, the queuing time, the WQ. Now, how do you do that? One, look at the formula. Look at the formula for the waiting time. WQ is actually lambda over mu into bracket mu minus lambda. Now, how do you reduce this? One is by increasing the employees. You see, the mu is actually the service rate. So if there's one server and you bring another server and another server, or you increase the service, what is going to happen is that this value here will go down. You realize that? The value here, the mu will go down. Okay. If you bring, the mu will go up. If you bring another server, the mu will go up and the entire formula will go down. So the time wasted or the queuing time will be cut if you bring another employee. Because it's a denominator here, the whole WQ will go down. So that is one way. One way is by bringing another employee, and it makes practical sense, yeah? If you bring another server, teller number 1, now we have teller number 2, teller number 3, now everything, service increases. And so you cut down the waiting time. Another, because of course, when you bring an employee, it's going to cost a lot of money. So because that can also cost money, you can decide rather to bring a machine. And in a fast-paced technological world, you can bring an ATM machine. In fact, these days, if it is a bank, for example, these days, you serve yourself. In fact, in most African countries, sometimes you have someone at the fuel station who is fueling your car. But in most European and American countries, you don't have anybody fueling your car. You fuel your car yourself. And so there's a machine that is there for you. So instead of bringing an employee, you can bring a machine. In this case, instead of entering into a bank and being served by the teller, either you are withdrawing or depositing, you now have a situation where you can deposit money. Just deposit money at the ATM or take money at the ATM, withdraw, either of them. Now, either of them is going to affect the waiting time. They are both going to cut down the waiting time, isn't it? Because what it means is that the lambda here, because the lambda here, if you bring a machine, the moment an employee arrives at the building, instead of going to queue for a human being to serve, he will quickly rather goes to the machine. And so what happens to the arrival rate? The arrival rate comes down. The lambda goes down. Okay, and as long as the lambda is going down, then the queuing time will also go down. And that is good news. So you reduce the queue. So both will reduce the queue, but the question is which one is better? Well, in this case, we need to go back to our original queuing time we had, recompute the average waiting time, recompute how much time has now been saved, recalculate how much money could be gained in option 1 and option 2. And then we compare in both options which one is giving us more time saved and more revenue gain. And then we can make a decision which of them we should go for. That's what we are going to do now. That is the essence of our presence for today. So please pay attention. I'm going to give you a scenario that will check up all these. Let's start. ShopRite, very popular busy center for most people in and around East Legon area. there's a lot of pressure sometimes at this place. People are going in, people are queuing, as you can see here, and all of that. So assume that at ShopRite, there are 2 customers, and 2 customers arrive every 12 minutes. 3 customers are served, okay, every 15 minutes. And currently, there's only 1 cashier. Quick, easy question. What is the average waiting time in minutes before service begins? Question A, what is the average waiting time in minutes before service begins? What is this question asking you? You can quickly tell us before we move on. Which formula is that? This is why you should know these things on your fingers. These things must be very quick, very easy. W is wrong. W is wrong. Emmanuel says, Belinda says L is wrong. So you got to know these formulas. You got to really know this formula. Okay, the answer is WQ. Average waiting time before service begins. You see, watch the word waiting time. That is WQ. Queuing. Waiting before the service begins. So it doesn't include the service. That is why W will not be the answer. Because W is both waiting and service. Okay, so you're being asked to find that. That will mean that you got to know your lambda. Please work it in your book along with me. Oh. What is your lambda? Okay. And what is your mu? Okay. What is a lambda? And what is your mu? Watch it. But first thing, you got to convert something because some things are in minutes here. You got to take them to hours. 2 customers arrive every 12 minutes. So the lambda will be what? If 2 customers are arriving every 12 minutes, what you ask yourself is that, how many customers arrive in 60 minutes? Because we are dealing with hour. How many customers? 10. Perfect. How did you get a 10? Well, look at it. From 12, 2 customers are arriving every 12 minutes. So you ask yourself, if I divide 60 by 12, whatever I get, I'll multiply it by the 2. That's how it works. Okay. If I divide 60 by 12, whatever I get, I'll multiply it by the 2. And what did you get when you divide that? You get 5. And when you multiply the 5 by the 2, you get. So this whole kind of change of subject, this whole kind, you got to know this on your fingertips. You got to know so much that I don't even know how you got to know it again. Anyway, so if you do that conversion, you're going to get 10. So 10 customers will arrive every hour. So let's go to the service. Okay. How about the service rate? The service rate, it says that if 3 customers are served every 15 minutes. So what will be the service rate? The mean service rate. It will be 12. Exactly. Exactly. How? Because if 10 customers, there are 3 customers are served every 15 minutes. Okay. If I move 15 minutes upward, how many jumps will I get to 60? I need to jump 15 minutes 4 times, and I'll get to 60. So 3 customers, I need to jump it also 4 times. That'll give me 12. So the service rate is 12. Guys, if you don't learn how to do this conversion, you will be in trouble because once you get this lambda and mu wrong, everything down the drain. So now we know our lambda and we know our mu. Now we can go to the question and find the WQ. What is a WQ? The WQ formula is given and it is lambda over mu into bracket mu minus lambda. I want you to find this answer quickly. Okay, so you substitute it. It means you're going to have 10 over 12 outside, 12 minus 10, which is 2. That. Now, depending on whether you are using decimals or cancellation, sometimes, these things can be a problem. So I tell you today, okay, use, which one do I use? 4 decimals. Actually, I can cancel it and get a straight answer in minutes, but then you got to have it in hours before you multiply it by 60 to get it in minutes. So when you do that division, you get it from 4 decimals. You're going to get something in decimals. Let me see those of you who are working. Whatever you have is going to be in hours. Then you multiply it by 60 to get it in minutes. What do you get? Good. Stephen, you've done well. What you got, multiply it by 60 to get it in a minute. Please, if there are decimals, include the decimals. It's not a joke. If there are decimals, include the decimals clearly. And I think that if you look at most of the exams, they will tell you to use 2 decimal places. Okay, so let's assume it's 2 decimal places. What will be the answer in minutes? If it is 2 decimal places instead of the 4 decimal places. I know you are using 4 decimal places, but let's use 2 decimal places. And I think you got to be using 2 decimal places for our purpose. What will be the answer in minutes? No, it will not be 10.5. I'm sorry. No, check it again. Check it again. Yeah, somebody is thinking now. Belinda's joined the race. Okay. All right. So that is what you got to be very, very careful, because you will always be told the decimal. I'm saying that you'll be told the 2 decimals. All right. So let's see how it works. So this is it. You're going to get 25.2. And most of you got it. Belinda was the first to shake the mind. Yeah. So if you are using 2 decimals, you first get these 4 decimals, you convert it to 2 decimals, and then you're going to get 25.2 minutes after you multiply it. Guys, learn how to do this, because this we just did is key. If this is wrong, everything. 25.2 minutes. Ooh, that's cool. Now the question is, how do you, is this too much? Is this too much of a waiting time? Is this too much of a queuing time? Well, let's go to the question, because what you guys saw was just the first part of the question. By the way, the second part of the question, I will encourage you to do it on your own. I don't want to go there. It says, find the percentage of time that a customer has to wait. What is this asking you to do? You can quickly tell us. I don't want to do it, but I just want you to. What is this asking you to? Find a proportion of time customer has to wait. It's asking you to find what? The proportion of time the customer has to wait. Exactly, the U. And since you already know your lambda, okay, and then you know your mu, 1 is 12, 1 is 10, you can easily find that percentage. Okay, now let's go to the real deal. Here's a real deal. The story continues that management perceives that the waiting time that you computed in A above is not acceptable, and they are faced with 2 options. So this means that if you calculate your waiting time and yours is not 25 and it's rather 2, what you are saying is that yours is acceptable, because it has to be 25 for it not to be acceptable. 25.2. Management now want to cut down that time period. They can either employ an assistant for the cashier. So the current cashier, they will employ an assistant, or they rather open a second cash machine, just as we discussed theoretically. Now the former, that is getting an assistant, if implemented, will enable 4 requests, watch the English, will enable 4 requests to be served every 15 minutes. And the assistant will receive a monthly salary of 160 Ghana cedis. The latter, if implemented, will improve the arrival rate. Now you know which one, the latter. It will improve it to 1 customer every 12 minutes. Okay, so we have a preamble. Let's move on. However, it requires which one? The latter. The latter requires an initial capital outlay of 3,000 cedis, and the cashier who will man the cash machine, because the cash machine always must have somebody manning it. That man who will man the cash machine will receive a monthly salary of 250 cedis. Now, the shop avoids a loss anytime, a loss in sales of 80 cedis. When 80 cedis every month, okay, for each minute that the average customer waiting time is reduced. So what it means is that anytime we reduce the waiting time, we are avoiding a loss in sales. In other words, we have saved 80 Ghana cedis every month for every minute that we cut down waiting time. Now we come to the real question. Calculate the financial gain to the ShopRite under option 1. Forget about option 2 and advise management on this option. Ooh. So under option 1 and advise management. So let's go to option 1. What is option 1? Option 1 is that the former, if implemented, will enable 4 requests to be served every 15 minutes. So that word 4 requests to be served means that the former will affect which one? Is it going to affect the lambda or the mu? Will it affect the arrival rate or the service rate? Which one? Will it affect the arrival rate or service rate? Based on this sentence here, I need you to type me your answer. Which one? It will obviously, I see your good answers. It will affect the service rate, the U. So that means that original calculation we had, we have to go and alter the U. Okay. What was the U? If you can remember, the U was 12 customers, and now we got to alter that. It will not affect the lambda. So that first option, we leave that part for the lambda, and we affect the mu. So we have to recalculate. And what did it say? It says it will enable 4 requests to be served every, watch it, 4 requests to be served every 15 minutes. So you have 4 requests every 15 minutes. So now we are going to have 4 requests of customers every 15 minutes. So which means that how many customers are we going to get every 1 hour? You always have to think in these terms. 16, perfect. Steven, you're along with me. So now, you see how now these things are becoming easy in your head and you're answering them very quickly. So you're going to have 16 customers. So now new is no longer going to be 12. It will now be 16 customers per hour. But then the lambda will remain the same. And so with that in mind, you got to recalculate the queuing time. Our new queuing time, let's call it WQ1, because that is option 1. Our new queuing time will be the lambda, which is still 10, divided by the mu, into bracket mu minus lambda. So the lambda will still be 10 over this time, not divided by 12, but rather divided by 16. So you now have divided by 16, and then you have 16 minus 10. Find the answer. Have it in 4 decimals and 2 decimals. Have it in 2 decimals, and then that will be in hours, and then you multiply it by 60. And that will give you in minutes. Remember the first one was 25 minutes. The second one, this time we haven't changed it. We need to check that. What is it? You got to be working. I told you to have a book from the onset. So when you multiply it by 60, what do you get? I know all these, but you should tell me yours. You know what somebody is doing? Because Belinda is giving all the answers, the person is seated, the person says, oh, they will give you the answers. I don't need to worry myself. Or the person might say that, I don't understand, but I will not ask anyway. Okay. Good. So when you work this, you're going to get 0.1 hours which one you convert, you're going to get 6 minutes. Okay. So you have 6 minutes. Do you realize that you've been able to cut the waiting time? It was 25.2 minutes. And now you've been able to reduce the time to 6 minutes. That is cool, mate. That is cool, yeah? However, we now need to find how much money we have saved at this case. So the first thing we've got to calculate is what is known as the time saved, TS. Write it down. The time saved is the original time, which was 25.2, minus the current time now, which is 6 minutes. Find the answer. What is the time saved here? You see, even if you're not with us, you should be taking your calculator and be punching these numbers. That is a participatory democracy. So you should be typing some in the chat. That will give you 19.2 minutes. So that is the time you have saved. Now, how much is that in monetary value? If you could remember, I'm just taking you back to the storyline. The storyline says something. It says that, and I know it's a little bit juggled here. It said that the shop, I know you don't see it fully, the shop avoids a loss in sales of 80 cedis per month for each minute that an average customer waiting time is reduced. So anytime you reduce the waiting time, you are saving 80. And we have reduced this waiting time by 19.2, isn't it? So we can now calculate the monetary gain of that. So the monetary gain will be that 19.2 multiplied by the 80 cedis amount that we gain for a minute, because if each minute is 80, then 19.2 minutes will be 19.2 times 80. What do you get? That's a monetary gain. 1536. Stephen and Belinda again. Fantastic. 1536. That's what you get. Now, that is monetary gain, not the net gain. How do we know that? Because we were told that somebody too must be paid. Okay? If you go to the storyline, it says that, and I know it's a little bit jagged, but you can find it. It says that, and the assistant, no, not this one. This one is the second option. Let's go to your first option. Okay. It says that if the former is implemented, it will enable for requests to be made, and the assistant will receive a monthly salary of 160. So there's a cost. So whatever money that you are gaining here, you got to take that amount from it. Now remember, this is monthly gain that we have had. So in order to find the net gain, you subtract the 160 from it. Okay. So the net gain will be that 1536 minus the 160. What do you get? That will be the net gain. Like the way some of you are really following, 1376. 1376. So that is a net. Now the question was, without considering the option 2, that was a question. It says that, it was here, calculate the financial gain to ShopRite from the option 1 and advise management on this option. We are not considering with the second option. Because this net gain is positive, advising management will be for them to go for option 1. We're not comparing it. I'll tell them that option 1 is good to go for. Why? Because the value is positive. So that's what you say. As since the value of the option 1 is positive, it's good to take the option. That's it. Cool. Finito. Let's go to option 2. Because it comes also with a question. Okay. Look at that. The next part of the question says, calculate the financial gain to ShopRite under option 2, assuming the initial capital outlay is sunk and advice management 2. So option 2 to look at it alone, don't compare option 1 and then advise. Again, we're going to check whether that's positive and then we advise management. So how do you do that option 2? Well, you were told that the latter, if implemented, will improve the arrival rate. So the latter will not affect the service rate, but it will improve the arrival rate to what? 1 customer every 12 minutes. Okay, 1 customer every 12 minutes. Now, if you can remember here, it was 10. The lambda arrival rate was 10, but now it is 1 customer every 12 minutes. So how many customers in an hour? I like the way you think. Stephen and Belinda again. 5 customers, okay, in an hour. Oh no, is it 5 customers in an hour? Yeah. Yeah, 1 customer. What is it? Lambda is going to be 5, right? Okay. So 1 customer every 12 minutes. So 5 every hour. And that is going to be the lambda. So your lambda is going to be 5. So when you now come back and calculate the waiting time, this time for waiting time, queuing time for 2, because that's option 2. You're going to have the lambda, which is now 5, but then you have to use the old service rate, which is 12. Not the 16 you just did, but then use the 12 into bracket, the 12 minus 5. You recalculate for the new waiting time under option 2. Of course, you're going to get it in hours, 2 decimal places, and multiply by 60. What do you get? Do some more. Okay? Do some. Do some. Do some. There is power in doing. Emerson, that's what he said. There is power in doing. You don't say that, I don't have the power. I don't know, so I can't do. No, when you do, then you have the power. That's how it works. It's the doing that gives you the power. Yeah. You get 3.6, exactly. You get 3.6 minutes. Remember that it was 25.2 originally. And remember that the option 1 brought it to 6 minutes, if you can remember. And this one has brought it to 3.6 minutes. So it is looking like the option 2 has really cut down the time by a significant proportion, which seems like is cool. Okay. Now, how do we find the time saved? The time saved, once again, is going to be the 25.2 minus the 3.6. What do you get? What do you get? The 25.2, you get 21.6. Okay. And now, what is the monetary gain? You were told that the monetary gain is when you multiply whatever you had by 80. So you get 21.6 multiplied by 80. That is the time saved per minute. So for this 21.6 minutes saved, you are gaining 17.28. 17.28. So that is a monetary gain, but there is a cost. Remember, it said that the person who manned the machine must be paid. Let's go back. So you were told here that the cashier who manned the machine will receive a monthly income of $250. So we need to get our net gain. Okay. So the net gain will be this 17.28 minus 250. And that gives you what? $15. Oh, I'm getting different answers. 17.28 minus 250. What do you get? Check again. So you get 1478. Okay. So you get 1478. Now, based on this net gain alone, do you think that they have to go for it? Do you think they have to choose option 2? Yes, they have to choose option 2 because you have a positive value, isn't it? You have a positive value. So looking at it on its own, option 2 is a very good deal. But that question actually asked you, should they go for option 2, assuming, they made a point, assuming the initial capital outlay is sunk before you conclude. So because there was an initial capital outlay for installing the machine, and he's saying that let's assume that it's sunk. What does it mean for a capital outlay to be sunk? What does it mean? Okay, for it to be a sunk cost. Accountants, what does that mean? For initial capital outlay to be a sunk cost, what does that really mean? Sunk cost, it means that it cannot be recovered. So what they're implicitly saying is that 3,000 initial capital outlay, assume that it's not there. Assume that that cost is irrecoverable. So you're not going to punish the company with that cost. That's what it means. You're not going to penalize the company with that cost. Okay. And so the 1478 that you have here, it is good as it is. And so it is a positive deal. Now we go to the latter part of the question here. It says that now, assuming the initial capital outlay is sunk, that is still sunk, which option would you recommend to management? Okay. Now this option 2 is 1478. That is a net gain. Do you guys remember option 1? The net gain for option 1? Do you remember? If you were writing, you see, some of you might not be calculating, but you were writing, that's good. If you are writing, you will note that the net gain for option 1 was 1378. Okay. Yeah. Okay. So that is it. That is it. So if you can see that it's 1378, the first one. Okay. So if you open the second cash machine, the first one is 1478 and the second one is 1376. So what it means is that the second cash machine will bring in more money, okay, than if you employ a sales assistant. Okay. And so you will conclude. Most of you have written 1376. Is the 1376 the option 1 or the option 2? Oh, it's rather option 1. Huh? I think I made a typo there. Yeah. So the option 1, that is option 1. And the option 1 is employing, what do you call it? Option 1 is employing an employee, okay, going for an employee, a cashier. And so the option 1 then becomes the choice. Because, oh, sorry, the option 2 becomes a choice because option 2 gives you more earnings than option 1. Look at option 2. Option 2 gives you 1,478, which is more than the option 1, which is 1,376. So the cash machine actually brings in more money. And so that is the one you go for. Now let's go to the latter part of the question. The question says, and this is it, latter deeper part. After how many months will the management be indifferent? Listen carefully. After how many months will the management be indifferent? After how many months? Now watch it. If you want to know, indifference here means the management will be equal. Management will be indifferent between the two options when both are giving you the same net gain, isn't it? And that will mean that they will have to consider, because you see, this point, they didn't say that assuming the initial capital outlay is sunk cost. No, it wasn't said like that. And because that wasn't said, you have to bring the initial capital outlay into the picture. So let's look at the first option. The first option was 1478. And then the first option was 1478. First option was 1378, 76. So the first option was 1376. And then the second option was 1478. But that 1478, we need to subtract the initial capital outlay from it. Okay? Because after how many months, it didn't say that assuming the initial capital outlay is sunk. So this time we bring the 3,000, that must be subtracted. But the question is, after how many months? It's not about the money. So after how many months means that these two must be equal. That's what it's saying. But for that equality, you got to know how many months. So let's represent the month that it would take this one to be equal to the other one. We represent that by X. And then we represent this one too by X. So each one of them, I need to know how many months the two of them will be equal. That's what it means. Taking into consideration the initial capital outlay. So the X will be our number of months. Note the principle in which I've equalized them, but that is a beautiful part of this. I'm equalizing them because I need to know there's a period of time which I'm now representing as X, where this left-hand side will be equal to the right-hand side, taking into consideration the initial capital outlay. So what is X? Well, if you can see carefully, in order to get X, you got to group like terms. So when you group like terms, you're going to have what is already here, 1376X. Then you bring this one here, giving minus 1478X equals to negative 3,000. The negatives will go. Okay. I mean, when you do this one minus that, you will get a certain number. Check, tell me the value. You get, when you do this one minus that, what do you get? You get 102. Is it 102 or 102 point something? Yeah, we got 102. Okay, so you're going to get 102x equal to, that is negative 102. Okay, but I'm killing the negative because the 3,000 is also negative. So negative 102 equals to negative 3,000, giving you positive 3,000. And now if you want x, you divide both sides by 102, and that will give you 20. X will be 29. You check. 29 point something, 0.41. Is it 41? Yeah, 29.41. So this is the number of months it would take for the option 1 to be equal to option 2. Now, for you to know that you are correct, you know what you got to do? All you got to do is to take the 29.41, substitute it into the x, and see whether the left-hand side will be equal to the right-hand side. So you take your calculator, you multiply the 1376 times 29.41. Of course, the decimals will bring some slight differences. 1376 times 29.41. You get 40,000. Is it 29.41? Let me be sure. Yeah. You get 40,468.16. Okay, that's what you get. Now, what about this one? If you do 1476, you see, I'm even typing it on my calculator. Multiply by 29.41. Okay. You get 43,000, then minus whatever you get minus the 3,000. Okay. You get 40,409.16. So obviously there will be some slight differences here because of decimalisms. Okay. But the clues that you can see that they are all giving you almost the same amount. So it means that the 29.41 is truly the number of months it would take for that to be for you to be indifferent between the two options. But also it also means that it would take 29.14 months for 1 month to recover the initial capital outlay. So the question could have asked you, after how many months? There you go. It's even asking. Anyway, the question could ask you, after how many months would it take to recover the initial capital outlay if it was not a sunk cost? Okay, and you still need that 29.41 to make the decision. So, ladies and gentlemen, that is how you handle a queuing situation. Okay. That is how you handle a queuing situation, and everything I've done here, you can see that. So it will take 29.41 months to recoup the initial capital. Okay. Sometimes, in this very example, you can see that getting the machine was better, but sometimes you rather save more for hiring an extra employee than adding a new machine. As a manager, all that you do is that both are preferred to the original. We know that both are better than the original time. Okay? Because the original time of 25.2 minutes, was a lot of time wasting instead of the 6 minutes or the 3.6 minutes. But practically, life is not a straight line. Eh? In real life, it's very hard to choose between the two options. Why? Because other factors will be involved. For example, the idle time was not counted here. Okay, the employee's idle time was not calculated. The space that was lost when the machine came is not calculated. Certain portions of the building that were destroyed during the installation of the machine was not calculated. People who were affected through, who have to train the new person and the time wasted, all of these were not captured into the analysis. So in real life, certain things will have to take into consideration before the true analysis can be done. However, what we know and we should know is that queuing theory helps us to make a decision. It doesn't decide for us. It helps us to detect, to discern, to decode the cost trade-offs associated with an improved service. That if you want to improve your service, there is a cost and there is a benefit. Ladies and gentlemen, that brings us to the end of the entire Kabudo.